Okay, so for these, I think it's helpful to start by just identifying what's the base in each of these. So the base is the 3, the 5, and the 7. And everything else is having to do with how we're sort of transforming that original parent function. So let's just write what's the parent function for each of these. The parent function is y equals 3 to the x for this one. The parent function is y equals 5 to the x for this one, or you could think of this as y equals 5 to the negative x if you prefer to think of the exponential decay function. And this one, the parent function is y equals 7 to the x. So let's talk about part A. For part A, what's happened to this function is that I have done a reflection that is on the outside, so that is a vertical reflection. In other words, it's a reflection over the x-axis. But we also have shifted it 5. And remember that exponent is going to get order of operations previous to that minus sign on the outside. So before I reflected over the x-axis, I shifted, and since it's on the inside, I shifted it horizontally. And plus 5 would go left 5. So I've taken my y equals 3 to the x, I've shifted it horizontally left 5, and then I've done a reflection over the x-axis. Now, if we take a look at part B, it really depends on which one you're looking at. If you use this, then we have simply multiplying by 4, so it's a vertical stretch. Oh, I'm talking about the wrong one. Hang on. Let's come back over here. This is the one I mean. If we picture it like this, then the only thing I've done to that when I go back to what I started with is multiply by 2. So that would be a vertical stretch of y equals 5 to the negative x, which is an exponential decay function, remember, by a factor of 2. You do have the option instead of thinking of the parent function as 5 to the x, in which case the first thing we do is we do a reflection of y equals 5 to the x over the y-axis, and that actually gives us our exponential decay function. And then we stretch by factor of 2, which is again a vertical stretch by a factor of 2. Now for this last one, we have two things happening. The first thing is this 3 that is up inside with the x, and therefore it is a horizontal. And we have to decide, is it a horizontal stretch or compression? So in this case, I would call this a horizontal compression or shrink by 1/3, because remember, horizontal is always opposite of what you'd expect. But this plus 5 is happening on the outside, so this is a vertical change. And it's adding 5 means it's a vertical shift up 5. So this kind of gives you a chance to make a connection between the transformations that you were studying in Unit 1 and the new type of function that we're learning about here. And it also, in Part B, gives you a chance to recognize that, again, we have that reflection over the y-axis that'll take us between the exponential growth functions and the exponential decay functions. And the last thing that we're taking a look at on this particular page, before we move on and take a look at some applications, is something called the natural base E. So there are a lot of things out there that use the natural base E. It comes up in a lot of mathematical applications of exponential functions in life, and you'll also find if you go on to calculus that we really like this because it is easier to work with when it comes to differentiating and integrating functions. So this is something that you'll use pretty often. And the first thing I just want you to be comfortable with is that it, just like pi is approximately 3.14, et cetera, goes on forever. E is an actual number. It always represents approximately 2.718, et cetera. So when you work with it, you can always go find it on your calculator, and I'll make sure that there's a calculator link to E. Make a little note to myself right now to how you find E on your calculator, but you'll see that it's right above a button that says LN, which stands for natural log, which we're going to talk about when we get to logarithms. So you'll use that particular button to get this put into your calculator. But for now, I'm just going to walk you through this here so that you can check yourself when you practice. So if I plug in 2, then I'm going to get approximately 7.389. If I plug in negative 1/2, I'm going to get approximately 0.607. If I plug in 3 plus pi, I get approximately 4,647.932. And if I plug in 0.01, oh, hang on, I dropped my 10 there. This function is a little different. Notice this is a 10. So that's 10e to the 3 plus pi. And this right here is 1,000 e to the 0.01, which is approximately equal to 1010.050. Now, I also do want to discuss the graph just quickly. This is not included in the notes, but I think it's good to think about that graph. Remember, E is approximately 2.71. So since this is bigger than 1, then we're going to have exponential growth when we graph this, not exponential decay. And so roughly, it's going to look like this graph. And this is still going to be at 0, 1, because if I do e to the 0, I'm still going to get out a 1. So therefore, 0, 1 is on my graph. However, if I want to plot another point, for example, at 1, e to the 1 is going to be e. So we have 1e, which is, between 2 and 3. So somewhere up here, etc. So you're going to end up seeing that the graph of your natural base exponential function looks like all the other exponential growth functions in its general structure.